So for this example, we have the statements below and want to write the base case S1 along with the cases for the inductive step Sk and Sk plus 1. Where in the first case we have the statement Sn is 1 plus 2 plus 3 plus 4 plus all the way up to n minus 1 plus n is equal to n times n minus 1 over 2. That is, the sum of the first n natural numbers is n times n plus 1 over 2. And then for our second statement, we have that r cosine theta plus I sine theta raised to the power n is equal to r raised to the power n times cosine n theta plus I sine n theta, which is, as we may remember, de Moivre's theorem for complex powers. So I said we'd be looking at these again when we got to induction, and we will. These are the two things we're going to see arguments for using this kind of process. Where in our first case, all we're doing here is just establishing the basic notation. We're seeing what things like S1, Sk, and Sk plus 1 look like. These are always the three main pieces of an inductive proof. You need to show what happens at each of these three steps when n is equal to 1, n is equal to k, and n is equal to k plus 1, and then try and put them together with this kind of pattern to get your argument. So at S1, well, we're just talking about the sum of the first one natural number, which here is equal to 1, and based on our statement, that is going to be 1 times 1 plus 1 over 2. Or in other words, 1 times 2 over 2, or, well, 1. We're just plugging in 1 and seeing what happens to our statement at that value of n equals 1. Similarly, when we're looking at n equals k, well, we're going to plug in k. So we go 1, 2, 3, and then I'm going to skip some of these in here because we don't know how big k is. K is just a stand-in. All the way up to k, where we're saying that, based on our statement, is equal to k times k plus 1 over 2. And then finally, for our k plus 1 case, we're going to do the same sort of thing. We have 1, 2, 3, and we're going to go up to k, but we're going to keep going past k up to the k plus first case, and as a result, on the other side of that equality, based on our statement, we're going to have k plus 1, where k was, times k plus 2, where k plus 1 was, and that's all still going to be divided by 2. Where a couple things to note with this process. For one, when we're talking about that value k, we're kind of saying here, give us any value. Notationally, it doesn't really mean that much of a difference in terms of using n, but we do like to note that we're not really talking about that n value in particular. That n's kind of a stand-in for the idea that it goes on and on forever, whereas k is just one particular value. It's a notational trick. It doesn't actually mean a great deal, but it is good to be a little bit specific and a little bit careful in that way. And then going into that k plus 1 case, we're not saying that k plus 1 is true at the outset. We're just defining what k plus 1 looks like. And when we get to a proof later, our goal is going to be to take something that we get from up here and use it to show that this has to happen, assuming that those two. Where, in particular, there's one other process that we have called strong induction. We're not going to see it in this section here, but it's worth mentioning that when we look at inductive logic, technically speaking, we are talking about what happens at 1, then at k, then at k plus 1. If we want to make it a little bit stronger, we could say that we get 1, where 1 is usually true, we'll see that later, and then we talk about everything up to k instead of just jumping straight there. Where we would want to talk about all the terms up to that if we had something like a recursive argument that we needed to show. We need to show that a recursion held or gave some other result, because in order for recursion to happen, we need all the pieces. You don't usually use strong induction unless you absolutely need to. It's kind of improper, but it's worth mentioning. Anyway, it's more detail than we need right now. That's really all we're getting here, is just setting the notation. For our second case, Well, it works in essentially the same way. We're going to look at our values for S1, Sk, and Sk plus 1, where S1 is, again, it's a pretty basic statement, and it almost always is. Here, that is the statement that r raised to the power cosine plus I sine, which for the sake of brevity in this case I'm going to write as CIS theta, raised to the power 1 is equal to r to the 1 times CIS of 1 times theta, or if you prefer, and most people would, r cosine plus I sine. And again, I'll talk about this later, but it's incredibly rare that S1 isn't kind of a pointlessly obvious statement, but we do still need to be sure that, well, you can get on the staircase, as it were. Anyway, for Sk, same sort of flavor as up there. We're just going to take all of our things with n and plug in k, where we're remembering that k is kind of just a stand-in for some general value along the pattern. So we have r CIS theta raised to the power k, which ends up being, well, it's not quite as clean, but it is still something. R raised to the power k times CIS k theta. Again, we're not necessarily saying this is definitely true, we're just plugging in k and seeing what that does to the overall pattern. And then finally for the k plus 1 case, well, you do the same thing. R CIS theta, now raised to the power k plus 1, where this, based on our pattern, is going to end up being r raised to the k plus 1 multiplied by the not very nice term CIS of k plus 1 times theta. But again, it's just plugging in those values. So this is the setup. These are the types of pieces we're looking at when we're going to make an inductive argument. And the next thing we're going to see is, well, how we can do that. That comes next.